Hello, my name is Kapil. I work for HelpShift, and let's just do a little poll. Like, how many of you know what core-async is? Show of hands. Okay, good. So I don't have to do a lot of explaining. How many of you know what Kafka is? Okay, great. So this talk is going to be about building reliable, scalable services with Clojure and Core.async. But it is not about building. I won't talk about the scalable part. It was just for SEO purposes. And I'll be just talking about the reliable part of the things. So, few things about me. I'm a staff engineer at HelpShift. HelpShift is a mobile CRM company. We help apps connect to their customers, and we have a library that sits inside the app. And here are some numbers on the scale. We have around 600 million active users monthly. We have 60K requests per second coming in our infra. We have 500 GB of data daily, somewhat. So, like you can see, like there is a scale problem, somewhat. But how do you deal with scale reliably, right? So there are like 3 points that we are going to talk about, and we are going to build a service which satisfies these properties. The first is fail fast. What does that mean? So when your service sees a non-recoverable error, you say, okay, I don't know what to do, let's just stop. Resilient means let's do retries because I can recover from this error. And back pressure is just, I know I am in a degraded state, but I'll wait for some time and then try again. So let's take a look at problem and then we'll start building things from that. So we have lots of Elasticsearch updates in our system, but we don't necessarily want them immediately available. So what we are doing is we are adding a level of indirection, and we are saying we'll push them to Kafka. And Elasticsearch happens to have a bulk API which is more performant than writing single updates. So what you're doing is you're pushing all your updates to Kafka, and then we have this bulk service which has question marks, which will consume them and run the bulk API. Now what we are going to do is do a live demo of how to build this service from scratch. Okay, so fingers crossed. Okay. So is the code visible at the end? Okay. So the problem again. So we are consuming bunch of things from Kafka, and we have bunch of question marks. We don't know what that is going to be, and we have Elasticsearch. So this is how the code will look like. I want you to focus on the highlighted parts because we just care about that right now, and don't go into the details of how it works. So we'll walk through the highlighted parts. So we have init es bulk updater, which is just a function which will return a database connection, which we will use later on. It has two callbacks. One is for success and one is for error. Okay, and we have a do seek. What it is doing is it is consuming from Kafka. There's a topic Elasticsearch updates, and it is performing a bulk process update to your Elasticsearch connection, and we are passing a message to it. Okay. To go into the detail, what the Elasticsearch connection and the client is doing is it will call the callback success and error based on the condition it will go into. So basically, if there are like certain number of messages that the client sees, Elasticsearch client sees, it will say, okay, I know now I need to perform the bulk update and let me start. So it will say es bulk start, and then once it succeeds, it will say, okay, es bulk has done, and like you can do whatever you want. The problem here is when the bulk actually starts, we don't want to consume anything from Kafka because you just don't want to consume because you don't know what your response is going to be. Is it going to succeed? Is it going to fail? You never know. And if you consume too many messages in that process, you stand a chance to lose those messages, and that's not what we want. We want a reliable step-by-step succession of states. So since we can't have a demo with Kafka and Elasticsearch running this, that will be too crazy to handle. So what I've done is we have created a stubbed version of the same thing. What you see is what the external systems will generate events. The order is as they happen. So what you are seeing here is there are 2 Kafka messages that are generated, and after that the bulk has started. So assume that the Elasticsearch client is configured to run the bulk update after 2 updates, okay? And once that happens, it will respond with success. This is like our happy path. This should work with the current code. Let's try to run it. Switch to REPL. Okay, so these are your input signals, one on the top. That's how they were supposed to, they got generated. And the second is system behavior. That's how they got consumed. So this is a happy path. This is how it should work. But let's see some strange cases which we will have to handle. So if you see the part in the red, there's a Kafka message that has arrived between when the Elasticsearch update started and it ended. We don't want this, but we can't handle external systems. That's how they got generated by our traffic. So what can we do with this? Okay. So if we run this without the solution, what is happening here is you're consuming messages from Kafka, your bulk starts, and there is a message that you don't want, right? Now this is a problem. So like all problems with Clojure, when I don't know what to do and when I don't know how to handle state, I just push an atom in it and hope that it solves the problem. So we have an atom. What we are doing is on the success callback, we are just setting the state of that atom to your success state. And what we are doing here is in your doseek itself, we are saying, okay, I know the bulk has started because we have a check saying is your success equal to ES bulk start, and then we are waiting forever for it to change to success, right? This is like a very primitive way to do it, but it works, right? So why not? Let's see if it can withstand more cases like this. So we have one more condition where the response is not success. The response is ES got a slow response. ES has just slowed down. Okay. So will this work now? Because we are just waiting forever to get a success response. So this will go on waiting and like the service won't do anything, right? This will just block forever because ES has just responded with whatever it can and we haven't handled error conditions, right? So if we run this, our REPL is going to wait forever. That's a tiny mini buffer, but basically my REPL is hung now. It's not doing anything. So to handle this case, now we have to add some more conditions. Here I am saying if the success response is bulk success or if there is an error, continue. Okay. So if you run this, now it is doing what we want it to do. Basically, the pattern to see here is, if anything is correct, is your two ES events, start and something else, should coincide, should be consecutive. There shouldn't be anything between those two. So this works great. So let's push it further and see if it can handle more cases. Now we add one more case where we are saying the bulk has started and it succeeded now. It's great, like things are back to normal and ES has recovered, but let's try running this. So you have a bunch of like starts and responses. So you just pay attention to the stars, the Kafka messages with stars. So if they are like being part of the are they coinciding with the ES bulk updates or not? So 3 and 4 here are behaving correctly. The 5 is again went bad. It's saying, okay, I can coincide with your bulk update. Even though we have handled it and we know that it should work, it's not. So what went wrong here? So I won't go into the detail of debugging this, but what is happening here is you need to reset the states of both your error and success. Because once they are set, they are just set to those values. Like we just saw one error and after that everything recovered. But we still have a check for the error, right? So it's passing and it's letting all the Kafka messages just flow in because it doesn't know if there's a coinciding update happening or not, because we have a state which is lingering. So this is a problem, right? It's clear that we can't handle all of this with just an atom. We need something more. So let's take a step back and try to understand core async. So I don't know like if we should go through this or like is everybody comfortable with core async? Do they know what this code is doing? Raise the hands. Okay, so we'll quickly go through this. So basically what core async lets you do is lets you talk between two processes. That's fundamental principle of core async, which is also called CSP, communicating sequential processes. So what we have, the core primitive is a channel. So we have a channel called C and we have two processes. Now these processes are special, we will call them Go process. The first process is what it is doing is it's putting something in a channel C, and there is one more process which is just reading from that channel and printing a message. If we run this, we'll get a message. Message from channel C, this is the message. Now there are two properties of any channel. If your channel does not have anything to read from, your reads will block forever. Right? They will just stay there waiting for a message from a channel. And if your puts don't have a consumer, the puts will also block because there is no consumer. So there is blocking on the both sides. If there is no producer, the consumer will block. If there is no consumer, the puts will block. So let's try out if a case where your puts will block. We have a channel called C1 and you are putting two messages, message 1 and message 2, and let's see what will get printed. Do you think second put succeeded will print here from the things we know now? Okay, who all thinks that second put succeeds will print? Okay, great. Everybody has an understanding of core async now. So it of course didn't print because puts are blocked because there's no consumer for the second message. Same thing for your consumer. If there is just one single put and there are two variants of the same consume, only one will succeed and the other will just keep waiting for another message to consume. So we have these semantics of blocking where we can make processes block on something and wait for that message to come. There is another thing called alt, where you can choose between two channels and say, okay, give me first thing on either of these two channels. I care about just first thing that comes up. So what we are doing here is we are putting messages of channel 1 and channel 2 randomly. So either one of the two will win. And then what we are doing is trying to read from either of the channel, whichever comes first will print. Okay, so this time channel 2, 1, this time channel 1, 1. So it's random. So you are just picking the first guy to come and like put the message. So this is all great, but how is it useful to fix our problem, right? This is like, we don't want coinciding Kafka messages when a bulk process is happening. So let's go back to our problem, and we have introduced a new thing called message channel, okay? And we have decoupled our bulk process update in a different process, and we are just pushing messages into a channel called message channel. Now if you notice, there are double banks, which just means you can use your core async API outside Go blocks. So you can use it in any process for that matter. So this is great, but this is not solving anything, right? This is just like you're adding an indirection without any help. It's not helping our cause. But let's see if this succeeds for happy path. So we have Kafka message 1 and 2, the bulk process starts and succeeds, great. But this was working anyways in the first place. So how do we improve this design to factor in errors and other states and coinciding Kafka messages, right? So we have our big old condition which was failing for our earlier solution, which was bunch of messages, then Kafka gets slow and there's a coinciding message during that time. Then we have some more messages, then there is one more Kafka bulk update, and there is a Kafka message coinciding on that, like a big condition. So what we are doing here again now is creating one more channel called control channel. Now this is just a naming convention where we are saying this channel won't have any data, it will just have signals to tell the other process what is happening. Now this control channel is, we are putting two things on this control channel, both the success and error messages, right? And we have a go loop. It is similar to the earlier go loop where we are consuming message from the message channel, but it is more complicated now. What we are doing here is consuming both from control channel and message channel. So let's walk through this from the simplest case, which is your message channel. What we are doing here is we have a alt, but we assume that only message channel will receive messages. So this is the code path that will be executed. So this is great, and this is consuming. Let's say there is a bulk, ES bulk start on control channel. Now the rules of alt are either of the channel receives a message, it will execute that path. So we switch to this part, right? And now this part gets activated, and what is our message is it's ES bulk start, and we say okay great, so what do we do next? So we change the state of our local go loop, which was state, which was init, and it changed to different things. Now it is ES bulk start, so we reach here and we are saying okay, what do we do next? We are saying we don't care about message channels anymore because I don't want to consume from that particular channel, and we are saying let's just wait for the next message on the control channel, which can be a success message or it can be an error message. Okay, so this works in principle. This looks like a good idea, but let's try to run it in REPL and let's see if it fixes all of our problems. And this failed. Okay. So we have a bunch of messages, the same thing, but if you see ES blocks don't have coinciding Kafka messages anymore. Okay, so this was the code part. So I'll switch to the slides. So you can see like how just basic primitives of core async let you do handle complex cases like this. Also, your testing becomes really easy because what you are doing now is you are containing all of your side effects and controlling those side effects in a consumption of channels. They are just switching states. So it's kind of like a state machine. This is also inspired by Erlang's Gen FSM, which also does something similar. So what you are doing is you're just pushing bunch of things in a message channel and updating your state and then checking if the state is correct or not. Okay, the scale part. So the first version of this service did 150 RPS. Now it has been in production for 2 years. It is now doing around 5K RPS without any major changes to the code. Another advantage of this structure is extensibility and maintainability. The first version was done in 5 weeks. We added support for Mongo, like a completely different database, just in 2 weeks because we had a consumption part right and how to handle the states and error codes. There is only one active maintainer now who's just contributing 20% of their time. The code is again like in production for 2 years. Lines of code is just 2K. This is including MongoDB part and the tests. Yes, we have like really nice coverage also for this project. Project is interestingly is also used as a library where your producer is just code instead of Kafka and they're using it for doing bulk updates. This is majorly used for migrators where you have to like generate large amounts of data. You're just pulling in this project as a library and doing that. To summarize, to build reliable system, we need to have predictable failures and to have good happy paths also. Use CSP core.async to decouple components, so you have you know what each component is doing and you are sure about it. Central FSM is a good pattern that we have realized, receive all data and control signals and take decisions in that central location. So this is also used in our business logic services, like we have implemented the same FSM for detecting agent presence if somebody is online or offline and doing reporting on it. This is done in the similar way. We have done routing and doing load balancing of workload using the same principles. So yeah, and this code is also available on GitHub. I'll mostly put out the link on Twitter, so please follow. Thank you.